Okay. These next couple of examples are going to look a little different with how they have the functions written. It's not just like x to the third plus an x squared plus an x plus a number and we're factoring or anything like that. They're actually going to have some parentheses in here. Finding the solutions to these kind are actually going to be a lot faster and easier than the ones that we were just doing because of how they're written, okay? But something that we need to talk about is in a graph can have one of two things. It can have turning points, or it can just like cross the graph, or it can just touch the graph. So a turning point would be when it switches from like going positively to negatively. Touching it just means it hits the graph, but it doesn't necessarily impact the direction that something was going. So what I'm going to have you guys write across at the top here is when a graph has even multiplicity at a root. So that would be when we said that number like x equals -3 showed up twice. That would be an even amount of multiplicity, but it could be that a root showed up twice or 4 times or 6 times or 8 times. That means that the graph at that root, at the even root, is going to touch and turn. If it has an odd multiplicity, which is something that we're probably more used to. We just haven't been writing out odd multiplicity because, like, if you found one root, well, it only showed up one time, but one is technically an odd number. So a single root actually is an odd multiplicity of 1. But roots could show up 3 times, 5 times, 7 times, and those would still be considered odd multiplicities. When that happens at that root, it's actually going to cross the graph. So I'm going to show you what I mean here, and then we'll look at some graphs to actually figure out, does it touch and turn or does it cross? So when I look at my equations, like I said, they are written differently. You can kind of see this one says -4, and then there's a parenthesis with x plus a half, and that's all squared. And then there's another parenthesis that says x minus 5, and all of that is raised to the third power. When you're trying to find your zeros, it's kind of already factored for us a little bit because of our parentheses. So we don't have to do that. What we need to just do is think about what happens if we start setting these quantities equal to 0. If you have a number sitting in the front, like that -4, if you set that equal to 0, it doesn't mean anything. So I'm not really concerned about that -4. I'm more concerned about the parentheses right now. If I set this x plus a half, what'd you say? Oh, x plus a half, if I set that equal to 0, and just think about what would happen if I solved for x. So I could square root both sides to get rid of the squared. But when I do that, and I'll just do it over here, I would start out maybe by square rooting it. I would have x plus a half. The square root of 0, though, is still just 0. I would get -1/2 for my answer. So the other one would be if I set x minus 5 to the third power equal to 0. Same situation, you could cube root it. The cube root of 0, though, is 0. So you kind of don't even have to really think about the roots. You just have to think about setting that internal piece equal to 0 and solving for x. What are you going to get for this one? +5. So here's how I'm going to write it over here, though. I'm going to say that my x's were that -1/2 and a 5, okay? But we need to figure out what the multiplicity would be. Look at your exponent. This is going to tell you how many times that root would have shown up. So the 1/2 or the -1/2 is going to show up twice. So I would write next to this multiplicity of 2. The 5 showed up how many times? 3. So I would write multiplicity of 3. When they ask where are they located, those are just the solutions but written as coordinates. If they're crossing the graph at the x-axis, there's no y coordinate. So it would just be -1/2, 0, and 5, 0. So just writing those as intercepts now. Now, using what we wrote at the top of the screen, we can answer the next question because it's asking which zeros are turning points and which ones would just cross the x-axis. So remember, turning points would be it touches and it turns there on the axis. Crossing means it actually goes through the x-axis and it starts to continue to go down or continue to go up. So when it's even, it touches and turns. So at 1/2, I'm going to say it touches and turns there. And then I'm going to say it crosses at 5. Because the 5 is an odd multiplicity, the -1/2 is an even multiplicity. And they are showing you that down here on this graph. They actually just put the graph in here for us. And we can see those zeros. They've got this one over here at -1/2 and this other one over here at 5. You can see how at that -1/2, the graph, like from the left side, was coming down. It hit the 1/2 and then it turned directions. It went up. And then it continued to go down again. And when it hit 5, it continued to go down. It crossed the x-axis and it just kept going down. So that's kind of the difference between touching and turning and actually crossing the graph. Crossing is not going to change the direction of the line on your function. Touching and turning will. It's going to switch the direction that your line was going in. So let's do one here from scratch. We want to find my zeros, and then we just want to be able to graph it using what we just talked about, using multiplicity and understanding if it's going to touch and turn or cross. So think about what we did before. It's already factored for us. We need to just think about these internal quantities and setting these equal to 0. So if you do that to the first one that says x minus 4, what are you going to get there? 4. And how many times did it show up? Good. And then how about the other one? And that showed up twice as well. If it's even, does that mean it crosses or touches and turns? Good. So we're going to say that this graph is going to touch or touches and turns, and it's going to do it at both of these. So it's going to do that at -3 and 4. So I'm going to go to my graph now. I'm going to put those points on, -3 and 4. And then I'm going to think about how this would look. I'm also still thinking about end behavior. So if I come back to this original equation, is this equation positive or negative? It's positive. And let's talk about how you would figure out if it's even or odd. Okay. Look at those exponents. If you add them together, like the 2 and the 3, we get 5, right? 5 is an odd number. So this would have an odd degree, which means we know they're going to be facing opposite directions, but the end is going to be facing upward. So my end behavior is going to be starting down and going up. Oh, it does equal 4. I can't do my math today. Thank you for catching that. Be nice, Abby. Okay, so it's positive and it's even, which means it would be facing up both times. I was thinking about the last one being 3 and 2. So they're both positive. So now when I think about what's happening here, I said that at -3 and 4, it touches and it turns. It doesn't cross. It's not going to go beneath the x-axis at those points. So it's starting up by being positive. So like the graph on the left-hand side is going up forever. When it came down to -3, it touched and then it turned directions. It does not continue to go down below. It starts to go back up. Okay. And then it has to come back down and touch and turn at 4. So it went up for a little bit and then it came back down. It touches and turns and then it goes back up. Kind of looks like a W. Again, I'm not being technical with my points in the middle right now. This W part, like it could be way up high. I don't know. I'm not going to look at that point on my table because that's not what I'm concerned about right now. Okay. Oh, that's next. That's not even in this section yet. Are you excited about that?
No.
Do you like to divide polynomials?
Well, they probably don't.
Do you remember synthetic division?
No.
Oh, it's like my favorite thing to do in math.
Really?
Actually, I love doing
Once I
synthetic
see it,
division.
I'll know it.
You'll see it and you'll be like, oh yes, I remember doing this. It's really easy. Okay, if you guys turn your page over, we're going to talk now about the intermediate value theorem, which is kind of going off of what we just went over with like touching and turning and versus crossing. We can look at a function and we could pick two numbers that are on a table, and it could be any two numbers that I wanted to. And I could evaluate them at my equation that I'm working with. And I can look at the answers that I get to understand, is my graph going to cross in between these numbers, or is it going to touch and turn? Like, is there going to be anything that happens there? So what this is saying up above in all of the definition, it says when you plug things in, if you have answers that have opposite signs, then there is at least one value between those. That means that there's at least one real root between the values that you're testing. So it would actually cross or it would touch the x-axis at that point, or in between those two numbers that I'm testing. If there's not a visible sign change, so if you get two negative answers or two positive answers, then that means there isn't a root that's located in between those two numbers. This is helpful when you're trying to maybe sketch a graph, or if you're trying to figure out, is it going back up? Is it getting really close to the x-axis, or what's it doing? So I'm going to show you how to do this. This first function we have says 3x to the third minus 10x plus 9. And we're trying to figure out if there's a real zero between the 2 points, -3 and -2 on my x-axis. So I need to evaluate my functions at these 2 points. We can do this two ways. You can plug in the numbers for your x's and like type that in as an equation. You also can type the function in on your table and then look at -3, what's your y value? Look at -2, what's your y value? Because that's going to give you the answer. So I'm going to write it out, and then we'll also do it on our table to practice it that way as well. So I'm just plugging it in. I'm putting it in for all my x's here. And now I just need to know what those answers are. Again, you can manually type that in, parentheses, and the -3 and the -2 in there. I'm just going to hit table, and I'm going to type in this equation. So 3x to the third minus 10x plus 9. And then I'm going to just start it at -3, and I'm going to go to my table and have my table just do all the calculating for me. Okay, and then I'm also right there, I can see my -2 value as well. I got -42. Did you guys get that for the -3?
Yeah.
And then my table's giving me 5. So looking at just those signs of the numbers, 1 is negative, 1 is positive. There is a visible sign change, which means that there would be a root there because it's going to cross the x-axis, because my y's, one of them was down really negative, and then the next one was up in the positives. That means that the graph had to travel up and it had to cross the x-axis for the y's to change signs. So I'm just going to write, yes, there is a root there. Okay, so why don't you guys try the next one? This is your function. You're trying to see if there's a root between 1 and 2. If there's a sign change between the numbers, because that means that your y, like as the graph is traveling along your y-axis, it crossed the x. What'd you guys get for an answer at 1? And at 2? So was there a sign change? No. So there's no root located in between those 2 points. If you guys have your table pulled up, where is there a sign change? At what x value? Nowhere?
Goes from positive to negative.
Yeah, like your y's. When do they start to switch from?
No.
Never.
They should eventually somewhere. I think you need to go into the positives.
I don't want to.
Yeah, no.
No,
Those
like
looks like
seriously.
5,000, 6,000.
Oh, so you know what? Then this one has no real answers. This one would only have imaginary roots because it's never going to cross the x-axis. I wouldn't want to find those. I would not want to find those. Those are going to have eyes involved. That means that, I mean, this is a parabola because it's squared, guys. This is squared. So that means that it's a graph that looks like this. I don't know exactly where it is, but it would never cross the x-axis. So you aren't going to see a sign change. Yeah, you could keep clicking and go forever on those tables. They just keep pumping out numbers for you.
They get higher and higher. No dirt. Why are you looking?
Okay, next piece.
Why are you judging, Izzy?
Understand the relationships between degrees and turning points. So I have a website pulled up. I have Desmos pulled up here. So I'm going to switch to that, and we're going to actually look at these together, and I want you guys to keep track of how many turning points the function has. Okay?
Do we gotta use Desmos at all this year?
Probably not, no.
Okay.
Oop, let me- Okay, so I'm going to type this in. It might be easier if I flip this around. Well, maybe. We'll see. So what's the first one say in our notes? We'll read it.
2x plus 1. 2x plus 1.
So difficult. Okay. Does this have any turning points? Meaning, does the line appear to go like this anywhere?
No.
No. So on your guys' notes, can you write 0 next to that first one? This one has 0 turning points. Whoops. Okay. Back. Next one. What's it say?
3x squared minus 8.
How many turning points does this one have?
3, 2, 1.
1.
What do you say?
It turns one time because it's coming down from the left, down to that vertex. It turns and it starts to go up. So that one has 1 turning point. Okay. And we've got one more.
That's all that matters.
What's the last one?
X cubed plus 3x squared minus 6x plus 4.
Okay. How do I?
What do you?
Oh, here we go. Cubed. I am typing it in. I had to figure out where a button was.
3x squared
Sorry, I'm not going fast enough for you.
minus 6x plus 4.
This one has 2 turning points.
2.
How did you know, Tanner?
Because it turns twice.
Did you know that before I graphed it?
Yeah,
How'd you know that before I graphed it?
because of the cube.
The cubed, the exponent, the leading exponent tells you something?
Yeah.
Yeah. Okay, so let's go back to our notes. Okay, so you guys said that this one had 0, this one had 1, and this one had 2. Look at your leading term and look at the exponent that the letter has. The first one's exponent would be a what? What does this x have as an exponent technically? A 1. This one has a 2, and the next one has a 3. How many turning points, like what's the connection between the exponent and the turning points?
Has 1 less.
It has 1 less every time. So if something had a leading coefficient that said x to the 8th power, how many turning points could it possibly have? 7. Now that would be the maximum number. It doesn't mean it has to have 7. It just means that it could have up to 7 turning points. So a function with a degree of n, so this could be any exponent, has at most that degree minus 1 turning points. no more than that leading exponent. It's always one less. But like I said, it doesn't mean it has to have all of them. It could, but it doesn't necessarily have to. But it could have up to that amount. All right, so if you guys turn your page over, we are going to take everything we've talked about from this section and combine it all together. Okay, so we're going to do all of the things. And behavior, we're going to find our x-intercepts. We're going to talk about does it touch and turn, multiplicity, and then we'll also talk about how many turning points should it have based on what we just went over. That's basically what all of this is saying, is that you're just going to kind of work your way through finding all of these things. You're finding, is it being positive, negative, even, or odd for your end behavior for step 1. Step 2 is finding your x-intercepts so that you kind of know some points that would be on your graph. We can also find our y-intercept by just putting in a 0 for all of our x's and then figuring out where it would cross the y-axis. And then we can use symmetry sometimes to help us with our graph. Not all graphs are symmetric though, so it only applies to ones that maybe would have some symmetry around the origin or the y-axis. And then we can also use what we just talked about to know how many times it should be possibly turning. Okay, so let's start down here on this one. First thing I want to know is end behavior. So is it positive or negative?
It's positive.
And is it even or odd?
Even. Oh, good stuff.
Why is it odd?
It's 2 plus 1. It's 3.
Yeah, this technically has an exponent of 1 on it. And so that x squared and then the other x that's in the second set would be up to a 3. So it's going to be odd. So what's our end behavior look like if you know it's positive and odd?
Down and then up.
Good. Down and then up. So I'm just going to draw those arrows to remind myself of that. All right, now let's try to find my x-intercepts. Remember, this was kind of already factored for you. So it's pretty easy to find those x-intercepts because we just set those parentheses equal to 0. And then we think about multiplicity. So if you set this first quantity equal to 0, what do you get?
-2 multiplicity 2.
Very good. And the second set?
Positive 3 and then multiplicity of 1.
Yeah, and most of the time I'm probably not going to write multiplicity of 1. I would only start writing it if it starts to be more than 1, like if it's a 2 or 3, 5, something like that. If we think about these as coordinates, this would be -2, 0, and this would be 3, 0. So those would be our first couple of points that we could maybe put over here on the graph. 1 at -2 and 1 at +3. Okay, now let's talk about with the multiplicity, if it's going to touch and turn or if it's going to cross. So remember, even multiplicity does what? Touches and turns. So I'm just going to write underneath here, I'm just going to write T and T. You guys good with that? For touches and turns? And then at 3, because it's an odd multiplicity technically, it would cross here. That means at -2, it's not going to cross the x-axis. So I'm just going to know that at -2, it's either going to be like a U shape right above -2 or it's going to be below -2. And then crosses means it's actually going to go through 3 and it's going to either continue to go up or down forever. Okay, now let's think about the y-intercept. To find your y-intercept, you're going to plug in 0 for your x's. And then solve it. So I'm going to take 0 in for that first set and 0 in for the x on the second set too, and I'm going to solve for that. You can use a calculator to help you if you don't want to do that mentally. But this should come out to be -24. And so my y-intercept would be 0, -24. Which is going to be way down here. But I at least know that my y-intercept is going to be down here somewhere. So to make it kind of fit my graph, I'm not going to go all the way down. I'm just going to draw a point down here to represent that that's where my y-intercept would be. It would be way farther on my graph if I was keeping this to scale. Okay, since we know back up here that it was an odd function because we counted our exponents, we said that the leading term, if I were to actually multiply all these things together, my leading term would have an x to the third. So what's my max number of turning points this can have? 2. So I'm just going to write this could have a max of 2 turning points. And then I'm going to try to graph this now with what I've known and what I have on my graph. So I know that at -2, it touches and turns, and that this will also probably be towards the end of my graph. So we said back up here at our end behavior that the left side of the graph started by facing down, right? So from -2, I'm going to go ahead and draw this side facing downward. Since it touches and turns at -2, that means it's going to switch directions at 2. So it's not going to go up, it's going to kind of come back down, and I'm going to connect it to that y-intercept point that I have at the bottom. Then what should it do?
Back up.
It's got to go back up because we got to get it back up there to the 3. And when it goes up through 3, is it going to turn back down or is it going to keep going up?
Keep going up.
Yes. Again, that's a rough idea of what it's going to look like. If I pulled Desmos back up here and I plug this in, it would actually show me the graph. It would be similar to this. Mine's not going to be perfect because mine's also not to scale. I didn't put my y-intercept exactly where it's supposed to be. All right, we've got one more to do. Do we have questions on that one, though? Okay. Last one here. Same thing. Let's start out end behavior. What do you guys think here?
Wait.
Final answer for $1 million?
No. For $1 million. Somebody help me out here.
Is it even or odd?
Even.
How do you know it's good thing you phoned a
Oh,
friend.
wait, I meant to say negative.
It is negative. I agree with that. And it is even. Again, we know it's even because of these 2's. Those together would be a total of 4, so that tells us that this would be an even graph. So if it's negative and even, what's my ends look like? They're both going down because even means they act the same, negative means they would be going down forever. Okay, let's solve for our roots. If you put this first set equal to 0, what do you get?
-1,
And any multiplicity?
+2.
And then how about the next one?
3 and multiplicity of 2.
Good. So they're both even multiplicity. Are we going to cross at those roots or are we going to touch and turn at them? Touch and turn, right? Because even means touch and turn. So I'm just going to go ahead and write touch and turn. And remember, these would be -1, 0, 3, 0. So let's go ahead and put those on here. Okay, let's think about the y-intercept next. So the y-intercept would be when we put in zeros for our x's. We got to solve that. So this would be -2 times a 1 times a 9. So -18. And so that would be 0, -18. Again, that's not going to fit on my graph, but I at least know where the y-intercept should be. Like I know it's not going to be up, it's going to be down below. So again, I'm just going to draw a dot down here to symbolize that point. What is the max number of turning points this graph could have? 3. So I'm just going to say max of 3 turning points. And let's see what we can do here. So we know it's negative and even, which means we know that both ends are going to be facing down. So I can go ahead and kind of just say like this is going to be going down. what's going to happen here at -1?
Gonna go back down.
It's going to go back down because it touches and turns there. It doesn't cross, so it's just going to flip its direction. It's going to go back down. I'm going to connect it to the y-intercept. Then what should it do?
Go back up.
Go back up, and what happens at 3? It's got to come back down. Okay, if you wanted to, you could extend these so it almost looks like an M. Any questions on the whole shebang?